Here we are with my third ever math lecture video. Hopefully this one goes a little bit more smoothly. I'm using some different software this time, and I am outside where there are no children. This is going to be about more on section 1.8. I already had the other video on section 1.8 sort of before, but I think it needs a little bit more explanation. Let's start with a few more examples and then a little bit of the theory and some important facts about limits that we'll look at later on. First of all, one-sided limits, that's what we're looking at with this first example here. One-sided limits are where we either approach from the left, which has this little minus symbol here. I hope you can see the cursor that I'm like highlighting this. Or we approach from the right, from the positive side, which has this little plus symbol. So let's look at part A, where we have the limit as x approaches 1 from the left. Here is what that means. So that means plugging in values of x that are like 1.8 or 1.9 or getting really close to 1, like 0.99, etc. And what you can see here with all these, if you plug in like 1.8 and then you plug 1.9 and then you plug 1.999, all of these y coordinates are equal to 1. So it's not exactly approaching 1 because it's already there, but you say for A, the limit as x approaches 1 from the left of f of x is equal to 1. Alright, then how about from the right? So that's this one here. So as x approaches 1 from the right, that means numbers like 1.2, 1.1, 1.1101, getting really close to that way is x approaching 1 from the positive side. Going this way was x approaching 1 from the negative side. Anyways, you can see as x gets closer to 1 here, it looks like the y coordinates, the output of this function, is just getting really small, and that's why there's this dotted line here, so you know there's an asymptote. So it looks like they're approaching negative infinity. You're just getting bigger and bigger negative numbers. So for B, the answer should be negative infinity, because y approaches negative infinity down that way. Then how about C? So for C, you need to have, this means a double-sided limit. And in order for a double-sided limit to exist, you need to be able to take values of x on either side of 1, meaning you should be, and it should be approaching the same thing. So when you plug in like 0.9 or 0.99 or 1.1 or 1.01, the output should be getting closer to the same thing on both sides. And if it's not, then the limit doesn't exist. So whenever you have a discontinuity here where there's a big gap between the two sides, the limit doesn't exist. And actually, I just realized I need to go back to part B here because there's something I forgot to say. I'm saying this is equal to negative infinity, but remember, infinity isn't a number. So really, this is just a special way of saying the limit doesn't exist, but it's a special kind of the limit not existing, because you're just saying that the output values get smaller and smaller, meaning bigger and bigger negative numbers, and so it's getting closer to negative infinity, but that's not, according to the formal definition of a limit, this doesn't really work. So we're usually just going to say technically or formally or something, this limit doesn't really exist. And that's maybe a better answer than saying it's negative infinity. Saying the limit is negative infinity is a way of describing what it's doing, but we're going to see why in a minute, why it's not a good idea to really say the limit exists. It's just a special kind of the limit not existing. All right, so let's look at D, E, and F, where we look at the function values around x equals 2. So let's see, let's do the one from the left first, like that. That's going to be part D here, the limit as x approaches 2 from the left. And you see here, what are the function values getting closer to? If you plug in like 1.8 for x, it looks like y will become, I don't know, 1.8 or something like that. It's hard to tell. And it's just getting closer and closer to y equals 1. So the result of the limit is 1, and the same thing is happening on the right here. So as you approach 2 from the positive side, the y coordinates are also getting closer to 1. So this is 1. And then let's look at the last one. In this case, they're both approaching 1 from the left and the right. So to do f here, we just are looking at values on the left that are approaching 2 and values on the right side that are approaching 2. Either way, they're getting closer to the number 2. So in terms of the formal definition of a limit, remember what that said is that this limit is equal to 1 if and only if that the values of f of x can be made to be as close to 1 as you want by making an interval or an open interval around x equals 2 that's small enough, that's guaranteed to contain only values of x that make f of x really close to 1. So you can get close to 1 on either side by just using part of the graph that is really close to x equals 2. So yeah, that checks with a formal definition of a limit. Hey, look what I can do in this software. I can say, look at these right answers. Bunch of check marks. Maybe I shouldn't really say that that's equal to negative infinity, so that gets an x. Because negative infinity, again, isn't really a number. Okay. Let's go on to how we can look at limits as x approaches infinity. And we're going to think of this sort of algebraically, numerically, and graphically, meaning using the symbols, also plugging in numbers in the table, and also looking at a quick graph. With part A first, let's do this one here. So as x approaches infinity in this function, e to the point 1 times x also approaches infinity, because e to a big number, if x is really big, is also going to be really big. And likewise, 100 times x cubed also approaches infinity. So as they both are really big numbers, like what's a really big number divided by a really big number? Well, it kind of depends on which one is bigger. If the denominator is bigger, the result is going to be less than 1. If the numerator is bigger, you might get a really big result. So one thing you could do is you could plug in some numbers into your calculator. And if you're finding the limit as x gets closer to infinity, just use a number for x that's pretty close to infinity. So here I did a few things with this calculator. So first I plugged in x equals 100 here, and when x is 100, then 100 to the power cubed is really big. That's a million, I think, and then times another 100 makes it 100 million. And then but e to the power 10 is what you get here. It isn't actually that big. So it looks like you get a small number. So that might make you think the limit is approaching 0 because you get this really small result because this denominator is so big if x is 100. And then you plug in, I'm just plugging in 200 here to see what happens next. And I get a result a little bit bigger than I had before. So maybe that means that the limit is not approaching 0. Maybe it's something else. And then if I plug in something like 1,000 here, then suddenly I get this gigantic number. This is 2.69. This e means times 10 to the 32. So this number is like a gazillion, bazillion, bazillion when you plug in x equals 1,000. So the reason for this is that it turns out, and I'm not going to explain why right now, but it turns out that if you plug in really big numbers into their inputs, exponential functions, like the numerator of this one, eventually always become much bigger than any kind of polynomial function, even though this polynomial function is really big. Ask me in class why, and I can try to explain it. But it turns out that that's true. So this is an important fact that we'll need sometimes. Oh, the pen's not working. Uh-oh. Uh-oh, it's getting laggy. There it goes. Okay, just want to show you what that looks like in a graph of this function. So here is a program called GeoGebra, which you might want to download. It's pretty handy for graphing things. So here's a graph of the function. We have e to the point 1x over 100 times x cubed. And here, yeah, it definitely looks like, hey, as x gets bigger, y looks like it sure is approaching 0. But these numbers aren't very close to infinity. Like, we want to see what happens to the limit as x approaches infinity. So maybe we need to check it out in a little bit more detail. Oh yeah, sure looks like it's still approaching 0 here. And oh, there it happens. Sometime around 200, when x is 200, suddenly e to the power 0.1 times 200 becomes very large, and it looks like the limit is approaching infinity. Let's try b now. So this one is a polynomial divided by another polynomial. So if the question is, again, they're both approaching infinity as x approaches infinity. Like x squared gets bigger and bigger, x cubed also gets bigger and bigger. The question is, which one is approaching infinity faster? So both of these get closer to infinity. And so let's see what happens as x gets really big. So again, you could do this by plugging in numbers, or you could make a graph. let's look at a graph here. So here is the graph of that function, 30x squared over x cubed minus 10. And you can see that if x is the cube root of 10, which is 2.2 or something like that, then this is undefined, and you get a vertical asymptote. But then as x gets bigger than that, then it looks like it's going down, getting closer and closer to 0. If we go further and further out, looking at bigger and bigger values of x, yeah, you can see that it really does just get closer to 0. And in this case, that's always going to happen when the power of the denominator is bigger than the power of the numerator. The x cubed is going to eventually be much bigger than x squared. How do you know that? And how do I know that the 30 is a lot bigger than the coefficient of x cubed, which is 1? But here's the trick. As soon as x is greater than 30, like if you do 31 cubed, that's 31 times 31 times 31, but x squared is just 31 times 31. So already the bottom is going to be kind of bigger if you ignore the minus 10. The bottom is going to be bigger than 30x squared because the extra x that this has is bigger than 30. So that's why higher power polynomials always end up dominating the lower power polynomials like the numerator. So this limit is going to be 0. I never actually wrote down the answer for A. I think I was distracted by computer issues. But anyways, the limit is 0. I'm sorry, it's infinity. What am I talking about? I'm not able to write properly. Okay, there's the answer to that. But with B, we have the limit as x approaches infinity of 30x squared over x cubed minus 10 is equal to 0. And before we go on to the next one, there's one more thing I want to say about this that will help us with C, is that if x is really big, like approaching infinity, then the 10 is going to be relatively small. Like if you plug in 1,000 into this, you're going to have 1,000 cubed minus 10, which is almost 1,000 cubed, right? The 10 is insignificant. So if we actually look at a graph of this in GeoGebra, which doesn't have the 10 in it, not letting me type. Anyways, if we did something without the 10, it would end up looking about the same. The graph would be about the same if x is really large. The 10 is insignificant compared to the x cubed and the x squared. But I'm having computer troubles. Anyways, let's look at C. So with C, let's think about this that same way. So again, we're talking about the limit as x approaches infinity, which means really big values of x. So if x is like 1,000 or 1,000,000 or something like that, then the 100 is going to be really small. It's not really going to matter. So you can just think of this limit as the same as the limit as x approaches infinity. It's basically going to be equal to the limit as x approaches infinity of 5x squared over 2x squared. Because also the minus 10x doesn't really matter, because if x is like 1,000,000, then 1,000,000 squared is 1,000,000 times greater than just x. So the negative 10x will also be insignificant. So this is actually just equal to 5 over 2, which is also known as 2.5. And let's make sure that that's what this looks like here when we graph it. Yeah, so it looks like the further out we go to the right, the closer it gets to about 2.5 right here, or 5/2. Okay, I'm going to pause it here and switch to another piece of software because this isn't working very well. Okay, so here's another good example of what I think is a good problem that really tests whether you understand limits or not. So we want a single function where all of these things are true. So we're going to try to graph something. Over here, and let's say we put let's make that be 1. Okay, so we have something that looks kind of like this. This is just the axes. Anyways, f of 0 is 2. Let's say that that is right here. So it has to have that point. So we know that much anyways. It's also given that f of 4 is 2, so that should also have that point. The third thing is the limit as x approaches negative infinity is also 2. So there's the line where y equals 2. And I don't know exactly what it looks like out here. Like, it just needs to get closer and closer to this line. It might come up from above or down from below or something between. So it looks like one of those, but I'll erase most of them until we get a better idea what it should look like. The limit as x approaches 0 of f of x is 0. So that means from both sides. Now we know that it doesn't actually have the point 0, 0 here because it has the point 0, 2, and it's only allowed to have one y value when x is 0. We just know that it's getting close to there. And I'm going to look around. Does it say anything else about negative numbers? No. So that means I can just connect this sort of dot to these other ones somehow. So there it has the right asymptote, the right limit as x approaches negative infinity, and it also has this right limit as x approaches 0. But it also has to go off from the right side from 0 here. It needs to be approaching 0 from both sides. It's also given that the limit as x approaches 2, the two-sided limit, is infinity. So that means that the closer we get to where x is 2, the further up towards infinity this is going to be. So that must look something, okay, not like that. It shouldn't ever cross this line, but more like that. And what else do we know? We know some information about the limit as x approaches 4. So the limit as x approaches 4 from the left means it is also approaching 2. So that means when you plug in like 3.9 or 3.99, the y coordinates should be getting closer to 2. So that means on the left here, it needs to connect up to that point. But on the right, the limit as x approaches 4 from the right side is negative 2. So that means that if you plug in 4.1 or 4.01, you should be getting closer to where y is negative 2. And it doesn't say anything about the limit as x approaches positive infinity, so that can be anything you want. I'm just going to have it wiggle around a little bit. Okay, so that looks like this now has all the properties it needs. So let's keep going. All right, so this is about properties of limits. These are pretty important theorems that, again, they're kind of the foundation of a lot of the theory of calculus. Uh, but mostly we just need to know how to apply them. We're not really going to prove why these are true. So the important thing about this that you should pay attention to first is this only works when all the limits on the right-hand sides exist. And of course, that's not always true for all functions. So if, for example, for number 1, the limit as x approaches c of f of x exists, then that means the limit on the on the left side also exists, and it's just equal to b times the other limit. And if you know that the two limits of f of x and g of x exist as x approaches a number, then if you want to add those two functions together to make a new function, then that limit also exists, and it's equal to the sum. Now, 4 is the one that people mess up the most. The problem is that it only applies when g of x is not approaching 0. So number 4 here implies that things like the limit as x approaches 2 of x squared over 3 plus x. If you know that both of these limits of x squared exist and the limit of 3 plus x exists, and you can trust me for now that they do, then the limit of the fraction exists, and it's equal to the limit of x squared as x approaches 2 over the limit as x approaches 2 of 3 plus x. So and x squared is just going to approach 4. 3 plus x is just going to approach 5. So this will be equal to 4/5. But that only works when this limit on the bottom exists and is not 0. So this doesn't apply to things where you have 0 over 0, for example. So the limit as x approaches 0 of, let's say, x cubed over x squared, the top is approaching 0 and the bottom is approaching 0. So this doesn't apply. So this equals, who knows, something. The theorem doesn't help. My computer is very slow trying to record and annotate a PDF at the same time. This is supposed to look like a question mark. It's just getting worse. Okay. So the theorem doesn't help, but you know what? You could just cancel out an x squared in this thing. As long as x is not 0, then x squared over x squared just cancels out. So it's actually just equal to the limit as x approaches 0 of x, and that's just equal to 0. So there's a lot of limits like this where the theorem doesn't help, because if you have something where the top is approaching 0 and the bottom is approaching 0, sometimes the result is going to be 0, sometimes the result is going to not exist, sometimes it's going to equal 5. It can be all kinds of things. And yeah, take a look at these other ones. And remember, with these videos, you want to pause it as often as you can. I'm going to get better about cluing you in on when you should pause it, but you should be reading the rest of these to make sure you understand them. And if you can't do that over my talking, you should pause it and read it, or open the book, or something like that. Okay, so let's look at a reminder of something from 1.7. This is a definition of what it means to be a continuous function. It's that the limit exists at x equals c. So that means that as you approach it from the left side, it's approaching something, and as you approach it from the right side, it's approaching the same thing. So on both sides, it's approaching the same value. And it also means that f of c is equal to that same thing. So you have to have a filled in circle there where f of c is equal to that limit. So that means it's continuous at that point. So what this means is that you can apply these facts about limits that we just proved to show that functions are continuous. And I wanted to remind you of this because this is the way you can prove this next theorem if you wanted to. So, for example, with number 1, as long as f of x is continuous, that means the limit of f of x exists everywhere and is equal to the value of the function everywhere. So that means that you can apply this theorem 1.2 part 1 to it to find the limit of b times f of x, and when you find that, it's equal to the limit of f of x times b itself. So basically this fact will be true. So as long as this fact is true at every point, that means it's continuous everywhere, because you can use this theorem to find the limit. And likewise, you can use that to prove the rest of these if you wanted to. Now, this next one says that if you compose two functions, then and the two functions are continuous, so the composition of two continuous functions is itself always going to be continuous as well. Also, if you have a function that has an inverse, then its inverse function is continuous. And again, we're not really proving this, we just want to know how we can use it. So why are these facts useful? Well, they can tell you that a lot of functions are continuous. So for example, if you know that a certain function is continuous and another function is continuous, then you can get more complicated functions by composing them or adding them and multiplying them, and that's always going to be continuous. And what's nice about knowing that functions are continuous, well, when you know that, it means it's easy to calculate their limits, because to find the limit of a continuous function, you can just plug in the thing. So like, you don't actually have to think about values of f of x near c. You can just find f of c, and it's going to be equal to that if your function is continuous there. So here's some examples of some basic continuous functions. Linear functions are continuous. You can draw them without lifting up your pen. Exponential functions are continuous. Sine and cosine functions are continuous. So let's use this knowledge to try to answer these questions. So can we conclude if this f of x function is continuous or not? Well, first of all, e to the x is continuous. It's the basic exponential function. Is sine of e to the x continuous? Yeah, so how do we know that? Well, it's because sine is continuous, and so if you do a function composition of a continuous function with another function that you know is continuous, and the result is continuous too. So it's a composition of two continuous functions. Now sine squared of e to the x is sine of e to the x times sine of e to the x. That's what this notation means. It just means the result of sine multiplied by itself, or squared. Um, Now, how do I know that that is continuous? Well, this is a continuous function times another continuous function. And theorem 3 here says that if you know that these two functions are continuous, then when you multiply them together, that result is also continuous. And this is our f of x. Okay, so that sounds good. So it is also continuous. Okay, so you can make all kinds of complicated functions like this by composing and multiplying functions, and the result will still be continuous. So if g of x is any polynomial, well, let's start off with what we know about linear functions. Linear functions are always continuous. So, for example, that means be over here, I guess. We know that just the regular old equation y equals x is continuous. And what does that say about y equals x squared? Or just f of x equals x squared. Well, x squared is x times x. So that means x squared is the product of two continuous functions. So that's going to be continuous too. We also know that if you multiply that by any constant, like a2 times x squared, that is continuous too, because that's a constant times a continuous function. And you could also take that and multiply it by x again. So like for the same reason, if you do some constant a3 times x cubed, that's just a constant times x squared, which you know is continuous, times x, and x squared times x must be continuous because they're both continuous functions. So you can keep applying the same logic to build up any old polynomial you want. You can say that, we're calling it g here, g of x equals a to the n times x to the n is just the product of n continuous functions, so that's continuous, and then you can add that to however many other terms you want. My computer is so hot right now that it is melting. I hope it's not melting, but it is hurting my hand. I'm going to open the back to give it a little bit more air. Hope I don't burn myself, and I hope my computer doesn't melt. So yeah, this is continuous too. So any polynomial is a sum of some products of a bunch of continuous functions. You can just build up each part of it from x and by multiplying by constants. Okay, how about C? Well, let's look. Part C here is you have a continuous function on top, because all linear functions are continuous, and a continuous function on the bottom, because that's also a linear function. So is the result of dividing them always continuous? Let's go back and look what the theorem says about that. It says that f of x divided by g of x is continuous, provided that the denominator is not equal to 0. And actually, if the denominator is 0 on the interval from negative infinity to infinity, then that gives you, that means the function will be undefined there. And if a function is undefined on an interval, it can't be continuous there because you can't draw that part of the graph. So this is discontinuous at x equals 1/3. Because if x is 1/3, that makes the denominator 0. H of 1/3 is undefined. So the answer to the question is no, it's not continuous on the whole thing. You could say it's continuous from negative infinity to 1/3 because the denominator's not 0 there. So both of these are intervals that don't actually contain the thing that makes it discontinuous. So the denominator 3x minus 1 is non-zero for all of these values of x. Okay, so what about D? So D here is the same idea. It's a fraction, and it's discontinuous if the denominator is 0. But is that denominator ever 0? Is x squared plus 3 equal to 0 for any real numbers x between negative infinity and infinity? And the answer is no. X squared is always greater or equal to 0 for any x, because if x is negative, you square it, it becomes positive. If x is 0, 0 squared is 0. And if x squared plus 3 is always greater or equal to 0, if x squared is always greater than or equal to 0, then x squared plus 3 must be greater or equal to 3. Because it's 0 squared, so something greater than 0 plus 3. So if it's always greater than 3, it can't be 0, so this denominator is never 0. And if the denominator is never 0 on the interval from negative infinity to infinity, then that means this is always continuous, the fraction result of dividing them. All right, so those are the examples I want to do. I kind of want to point out that you can approach these problems from a variety of ways. You can do it sort of algebraically like I'm doing here, using the formulas themselves and these theorems which tell you about those formulas. It also helps to look at a graph whenever you can. A graph will help you understand it. And of course, you can also just use a calculator to plug in some numbers and see what happens. The more you combine these approaches, the better you'll have a complete understanding of just how functions behave in general. And I'll see you in class. Thanks for watching.